here, and we are looking at a review of some Calc 1 topics for that great first test that you might be finding yourself studying for right now in college, or maybe Calc 1 in high school, so we'll just see about that. All right, so the first part of this three-part review deals with limits, okay? So limits, obviously, you're going to be having them all over your first test, of course. So the first idea, remember, is the plug and chug. So when you find the limit as x goes to something or y goes to something, plug the number in and see if you get a value. So for instance, on this first one, I plug pi over 3 in, tangent pi over 3, and you know us calc teachers, we love to throw in some trig ones just to make sure you know that unit circle of yours, because as I said, super important. So the tangent of pi over 3, remember that's the tangent of the 60 degree, so he's the bigger of the two, so that's going to give me radical 3. So I end up getting pi over 3, radical 3, and guys, that's it, done. Merry Christmas, Happy New Year, right? We're done. You could write it like this to be like, oh, I'm going to be so clever, but you know what? Is what it is. Okay, so this next one down here, you plug 0 in, you get 0 over negative 5, and of course we know that's 0. So I'm really hoping the plug and chug ones are the easy ones for you. Then we move on, and you might get some that say, okay, we want a left-hand limit or a right-hand limit, and usually those are set up around piecewise functions. So for instance, let's say you have a piecewise function, and you are told that 4x minus 5 for x's that are less than or equal to 1, x is greater than 1, gives me the square root of x plus 2, whatever that is. And if they ask you for the limit as x goes to 1 from the left-hand side, remember that's coming from the left side. Less than, that negative is coming from the left side of 1. So just plug the 1 in. And when you do that, you get 4 times 1 minus 5, which is negative 1. If they ask you for the limit as x goes to 1 from the right-hand side, yep, you got it. You're going to use the one from the other side, right? The greater than 1. When you plug that in, you end up getting the square root of 1 plus 2, which we all know and love to be 3. All right, so that would be the left-hand limit, negative 1. Right-hand limit is 3. But if they asked you what's the limit as x goes to 1, you're going to tell them it does not exist. Because as I hope you remember, if the left-hand limit doesn't match the right-hand limit, it's a DN'er. Alrighty? Okay, so now we're going to move on to those special cases. Alright, so now you say, okay, well, it looks kind of like what we were doing. So we're just going to plug the 2 in. But when you plug the 2 in, you get a 4 minus 12 plus 8, which would give me 0 in the numerator. Plugging the 2 in the bottom gives me 0 in the denominator. Whenever you get 0 over 0, it means you can do something. You got to do something. Maybe you got to factor. Maybe you got to pull out a trig identity. Something. You got to do something. So when I think about what I have to do, I'm going to factor this. I get x minus 4, x minus 2, over x minus 2. And yep, lo and behold, goodbye. Now when you plug in 2, you're actually going to get a value. So when I plug in 2, I get negative 2. So the limit as x goes to 2 of this expression is actually negative 2. You would see that if you graphed it, but I know how those calc teachers in college, right? You're not using that graphing calculator. You're not anywhere near that graphing calculator. So just note, if you get 0 over 0, it means you can do something. So check out the next one. You plug 0 in. Cosine of 0, you know what I said. We're going to throw some trig identities at you, right? So I put 0 in, I get 1 minus 1, which is 0. 0 in the bottom, 1 minus 1, which is 0. I got 0 over 0. I need to do something. 1 minus cosine x squared, that's a screamer, guys. That's a difference of 2 squares. So you could actually factor it 1 minus cosine and 1 plus cosine. Sitting over, of course, 1 minus cosine x. Goodbye. Oops, that was supposed to be a 1, not an x. You knew what I meant. Goodbye. Now when you plug 0 in, you get 1 plus 1, which we all know and love to be 2. We get 1 plus 1 because cosine of 0 is 1. So I'm hoping that, just a little stroll down memory lane for you. All right, and sometimes you get those radicals, and you're like, what the heck? But you can do those too. So check out the next slide. So you get the limit as x goes to 9 of x minus 9 over the square root of x minus 3. So like we said, put the 9 in. Get you 0 on the top, 0 on the bottom, so you know you can do something. The funny thing is this one actually can do one of two ways. You can multiply by the conjugate, so I can hit the top and bottom by the square root of x plus 3. In doing so, it's pretty cool because you're going to get x minus 9 in the top over, I think that's the square root of x plus 3, true statement. But in the denominator, when you FOIL that out, you're going to get x minus 9. And then, of course, you see the x minus 9's going, and my calc teacher would have taken off points if I didn't write limit as x goes to 9 there, by the way. So now I'm going to put the 9 right in on there, and then I get the square root of 9 plus 3, which is 3 plus 3, which is 6. Another thing you could have done for this particular one is you actually could have factored x minus 9. I know people think, what are you talking about, lady? You're crazy. But you actually could. That's going to get me the square root of x minus 3, square root of x plus 3. If you had done it that way, then right from the get-go, goodbye, and you could have just plugged in the 9. So either way, it's going to work. But oftentimes when you see the radicals sitting there and you end up getting a 0 over 0, you know you have to do something, and that multiplying by the conjugate does come in play there. So just take some mental notes with those. I hope that those special cases kind of have helped you a little bit. Now we're going to move on to some other special cases known as limits going to infinity. Okay, so here we are. We're going to infinity now. And hopefully you remember that really what we're finding are the horizontal asymptotes. Maybe that's something you remember from your pre-cal days. But remember, whenever x is going to infinity or negative infinity, we're really trying to find horizontal asymptotes, if they even exist. So a couple rules of thumb. If the power in the denominator is greater than the power in the numerator, the limit as x goes to infinity would be 0. And it really comes down to the fact that as x is going to infinity, the denominator is winning, right? So now you have little number over very, very, very big number. And little number over big number make very small number. And that's why it's going to 0. Now, for the next one, as x is going to infinity, notice that the power in the numerator is the same as the power in the denominator. So really, I mean, there's this whole, like, dividing by the highest power thing and blah, blah, blah. But basically, group those two guys together and simplify. I mean, that's really the key fact of the whole thing. All these other ones, I mean, they're nice and all, but 3x and x squared and 4, they're not going to do much with these other numbers. So you really are just focusing on the coefficients of those highest degrees, as long as the degrees are equal. And of course, you know, you're probably asking now, okay, well, what happens if the degree in the numerator is greater than the degree in the denominator? Well, then you don't have a horizontal asymptote, and you're actually going off to infinity. So that's not going to do you any good when it looks for horizontal asymptote. If you recall, in a graph, you end up having an oblique asymptote. What? Yeah, oblique asymptote. All right, so that's something to kind of remember. And sometimes, you know, us calc teachers, you know how we are. We like to be like, oh, x is going to infinity of, let's say, sine x over e to the x, all right? Well, remember, the sine x, he's on lockdown between -1 and 1. And as x is going to infinity, the denominator is really the one that's winning here, because you're taking e and raising it to a huge power, which again makes little number over very big number, which of course makes 0. So I always go back to, like, you know, who's winning when you're dealing with these functions. It's like, which one's really going to be winning? Is it the numerator or the denominator? The denominator's winning. Yep, we're going to 0. Alrighty, so that's basically as x is going out to infinity. All right, now we're not done yet, okay? Because what if you're going towards a number that makes 0 in the denominator, but a number in the numerator? So let's check out some of those. For instance, let's say x was going to 2, and we're just going to use like 1 over x minus 2. Very boring, I know. But if I put 2 in, for my x, I end up getting a number over 0. When you get a number over 0, you know you're looking at a vertical asymptote, okay? So that means your only options are going to be negative infinity, positive infinity or a D and E. Okay, so when you're dealing with vertical asymptotes, those really are the three choices you get. Kind of boring, I know, but that's all you get. Now, if you're going to a vertical asymptote and it's not telling you whether you're coming from the right or the left, all right, plug in numbers around the right and plug in numbers around the left. So in other words, if I plug in a number bigger than 2, like 2.0005, I'm going to get a positive number, right? If I plug in a number less than 2, like 1.99999, I'm going to get a negative number. Well, that means I'm going to positive infinity from the right-hand side. I'm going to negative infinity from the left-hand side. So since they don't match, we have ourselves a D and E. Okay? So you might be asking yourself, okay, well, when would they match? Well, if we have something like this. All right, so let's say we're going to limit as x goes to 0 of 1 over x squared. Well, since we're squaring the denominator, when I put a number in to the left of 0, I get positive infinity. I put a number in from the right of 0, I get positive infinity. So since they're both going to positive infinity, your limit is a positive infinity. So that's kind of how you work with those vertical asymptotes. And I'm hoping that you understand, like when I talk about getting a negative number or getting a positive number, basically you're just taking the value of x minus 2 around that number. So I'll do one more. All right, so as I go to 3 from the left-hand side, okay, so this time I'm going from the left-hand side. That means the numbers that are going close to 3 are like less than 3, like 2.9999999. You know the picture, right? You've seen pictures. Okay, so if I put a number like that in for my x, like 2.99999, 2.999 minus 3 gives me a negative value. And the reason why we're going to negative infinity, okay, is because a number over 0, a number close to 0, is infinity. I think you guys remember that, right? It says, you think about it, as I approach a number, as x is going to a value in the denominator that's a fraction, like 1/10 or 1 over 100th, this number is 10. This number is 100. So as you see, as the denominator is getting smaller and smaller and smaller, the whole value is getting bigger and bigger and bigger. That's why it's exploding. The other thing, don't ever forget your good old-fashioned vertical asymptotes, right? I mean, you've seen these before. The graphs, you know what they look like. It's not like you wouldn't know that. And if you don't, just act like you know it, right? Good times. So anyway, so as I'm going to 3 from the right-hand side, I'm going to positive infinity. If I was going to 3 from the left-hand side, I'm going to negative infinity. So if it just had the limit as x goes to 3 of this thing, that's my D and E. But if it's approaching it from the right or the left, then you have to decide, is it a positive infinity or is it a negative infinity? So you really do have to look at that. Alrighty. Now, another one that used to always get me were those absolute values. You ever remember those guys? So let's say I was going to limit as x goes to 4 of the absolute value of x minus 4 over x minus 4. And let's say I'm coming from the left-hand side. Okay? So when I look at absolute value, you always have to think about it. You really are looking at a piecewise function. And I think people kind of forget about that. Absolute value, you need 2, right? We always have had to have 2. So I would be like, okay, it's x minus 4 as long as x is greater than or equal to 4. Because if x is greater than or equal to 4, I get to keep exactly what I'm getting. Whatever value I get to keep it. That's why it's just x minus 4. However, if x is less than 4, that means I would have to plug the number in to x minus 4 and take its opposite. So what's coming out of there is actually 4 minus x. So if I'm coming to 4 from the left-hand side, that means I'm actually going to 4 from that piece. So it's 4 minus x over x minus 4, which of course is negative 1. So the limit is going to be negative 1. I think that's the one that messes some people up. Now, I don't know if your calc teacher is going to throw that kind of problem at you. I know I would. But, in college, I don't know what they're throwing at you. It's been so long. But anyway, that's what I would be looking at. Alrighty? Okay. Another thing with limits is that daggone sandwich theorem. Do you remember that, guys? So let me just take a minute about the sandwich theorem. All right, so here's that sandwich theorem, right? You know how lazy I am, right? I've got to take a picture of that thing. Basically, what it's telling you is that, look, if you have a function that's lying directly between two other functions, and it could be less than or equal to all the way across. So in other words, g of x is less than or equal to f of x, which is less than or equal to h of x, right? And it says for all x's in some open intervals containing c, except possibly at x equal to c. That means that if the limit of the g is going to L and the limit of the h is going to L, then f of x has nowhere else to go to but L. Of course it does, right? So the one that always comes up, and I always tell my kid, like, look, this one's a classic, right? It's called the x squared sine of 1 over x, right? And they say, okay, find its limit. And so when you set this one up, think about x squared sine of 1 over x. You know for a fact that the sine of any function is going to lie directly between -1 and 1. And I always talk about that in my class, right? That's huge. That you know that when you have a sine function, you're not getting bigger than 1 and you're not getting less than -1. So you hold that to be true. But you notice this has x squared. So what if I came through and just multiplied every piece by x squared? Well, now I have -x squared less than or equal to x squared sine of 1 over x, which is also less than or equal to x squared. Now, if I take x going to 0 of this side, I get 0. If I take x going to 0 of the right-hand side, I get 0. So that really leaves this guy no other place to go to but 0. So that's how you can kind of fish through with the sandwich theorem. And that really is like kind of all it really states. If you can pin your function between two other functions, right, which we were able to do here, right, between -1 and 1, and then I was able to get it between x squared and x squared, you could take the limit at the left side, limit of that right side, and if they're the same number, and that's the key, if they're the same number, then we can say, yep, the limit's definitely going there. If they are not the same number, then you cannot make the assumption. All you know is that it's between the two, but that's all you got, okay? So that's just kind of quickly what that sandwich theorem is all about. And oftentimes, you know you're going to be using the sandwich theorem, especially when they say this. Oh, you have 3 functions, and they show you this inequality, so you know you're dealing with the sandwich theorem. That one's going to a number, whatever that number is, and that one's going to a number, whatever that number is, then f of x has no other choice but to go to that value. All right? So I think that kind of sums up the limit side of hopefully what you've been reviewing, okay? So just kind of a recap, right? Plug and chug. Those are the money, right? That's the ones that I love those, right? Because you're plugging them in, crunching them out, yay team. The other ones we looked at is in the special cases if you get 0 over 0. If you get 0 over 0, you need to do something, right? Factor, trig identity, something to get that thing going. If you get a number over 0, you know you got yourself a vertical asymptote. So you just have to think, is it positive infinity, is it negative infinity, or is it a DNE? Remember, it's a DNE if the left doesn't match the right. And that works for piecewise too, by the way. And then, of course, if you're going to infinity, if the limit as x goes to infinity, there's your horizontal asymptote. And that's, of course, who's winning. Is the numerator winning? Is the denominator winning? Or are they both the same? The numerator is winning, no horizontal asymptote. The limit's either going to be positive infinity or negative infinity. The denominator is winning, then you got 0 as your limit. And, of course, if the powers are the same, you just simplify those powers. And then, like we said, we did the piecewise function, especially with the absolute value. Watch out for those. And then we also did the sandwich theorem. So, anyway, so I just figured I'd throw those out there. Nice little quick review on limits. And, yes, it's within 20 minutes. So you should be able to watch the whole video. Whoop, whoop. All right, next video is going to be about continuity.